will see. The link is for term 2. But no issues. Right now, we can start with the class.
Okay, fine. Okay, so let me start sharing my screen. Okay. Yeah. So from week 1 to week 6, what are the things we have seen so far? So in week 1 to 6, we have seen many things like matrices, right? Maybe in matrices, we have seen types of matrices, properties of matrices, determinants, operations on matrices, and things like that. And then we have seen system of linear equations, how to solve them, yeah. And then we started with what are vector spaces, subspaces, properties of vector spaces, right? And then we saw what are linear transformations, right? And how does again we go back to matrices, right? And how these linear transformations and matrices are related, how to represent a given linear transformation with matrices, and if we are given a matrix, how to get back to a linear transformation. Yeah, and then properties of linear transformation. So much about all these topics mainly we have seen. Okay. So now this week 7 is kind of a transition point, I should say. So we are kind of moving away from linear algebra slowly. Okay. So we are moving to the next level of linear algebra, I can say in week 7 and 8. And after that, we are moving to from week 9 onwards, we will completely stop linear algebra and move to multivariable calculus. Okay. So week 7 and 8 is kind of slowly shifting to the next level of linear algebra. Okay, so like first up to this, it's kind of one level, and then this is another level, and it is the next level. So this equivalent and similar matrices, we are just talking about matrices here. Okay, so just the properties of matrices where it is equivalent or similar. The application part of this comes in your next course, which is maybe MLF, I guess. In your MLF, maybe you will be seeing about finding eigenvalues, eigenvectors, diagonalization, and that place in diagonalization, you will have what are called similar matrices. So this is kind of a precursor to that. Okay. And this affine spaces and transformations, this is introduced particularly to understand that, see, vector spaces, vector subspaces, always you see that we are talking about spaces which are like only passing through origin. Okay. Now we saw that there are other linear structures also, right? Linear structure, any plane, it's like a linear structure, any line, it's like a linear structure, right? But we are not studying about them because the any line which is not passing through origin, we are not studying about it. But this affine spaces helps us to cover that part as well. So we are not going to study much in detail about this, but just an introduction to affine spaces and transformations is given. And then slowly we are moving to the next topic, length and angles in a products. Because so far what we have done, we have tried to add vectors, do scalar multiplication to vectors, and then transform one vector into other vector. These are the things we have done with vectors. So what is the next step on a vector? For a vector, what is the length of the vector? What is the angle of the vector with the x-axis, right? So these are the next things we should understand about vectors. So length and angles are the next topic. So in today's session, I will try to cover this and if possible, this as well. So these two topics is for the next session. All right. Okay. Fine. So first, before starting to what are equivalents in similar matrices, so let me recall a property which is the equivalence property. Okay, it is not just for matrices, it is the equivalence property which you have seen in Math 1. So do you remember what are the equivalent in an equivalence relation? What are the properties? Does anyone remember? There are three properties for an equivalence relation.
Reflective, symmetric,
Basically, reflexive, symmetric, and transitive.
Exactly. Very good. So you might have seen this equivalence relation in Math 1. So if those who don't remember, here is a quick recall of what is an equivalence relation. So a binary relation on a set A is said to be an equivalence relation if and only if it satisfies these three properties. What are they? Reflexive, symmetric, and transitive. What is mean by reflexive? Any element should be related to itself. Okay. And symmetric means if A is related to B, then it implies that B is related to A. Okay. And if A is related to B and B is related to A, then A is related to C. Right? So for example, maybe something, the relation, something like maybe, let's say some friends. Okay. So let's say A is a set of all friends. Then we are going to define. So friend myself. So my friend, if A is a friend to B, then B is a friend to A. If A is a friend to B and B is a friend to C, then A and C are friends. Something like that. Now, if I'm defining, then this is an equivalence relation, right? So there are several other ways in which you can define equivalence relationship. So if you want some example with mathematical expression, can anyone come up with an expression for example of an equivalence relation with a mathematical example? Anyone?
fx equal to y.
Matrix in the F X equal to one. Anyone? Or
Ma'am,
any other equivalence relation?
a equal to b.
Okay, so just the equality.
Yes, ma'am.
Okay, any other equivalence relation? The very common thing is the congruence modulo, right? I don't know how many of you remember the modulo. Don't remember? Okay, no problem. We are not going to use it. So those who want to recall, maybe you can go back to our math one and check that. So equivalence relation, you might have seen so many examples. The very common thing is the modulo, addition modulo you see. Okay, fine. Okay, so here, what is this equivalence relation doing? Okay. So we are going to define two matrices to be equivalent. Okay. So we say that A is equivalent to B if there is an invertible P of order n by n and an invertible Q of order m by m such that B equal to QAP. Okay. So now hold on this definition for some time. Let me first explain this definition here and then we'll see how this comes into play. Okay. So here we are saying we are taking two matrices of same order. Remember, A and B are of same order. That is the first criteria for defining equivalence between A and B. A and B are of same order. We say that A is equivalent to B if we are able to have an invertible matrix P and an invertible matrix Q. So remember, A and B are of order m by n. So this is also of order m by n. Okay, so this should be of order m by m and this should be of order n by n. Invertible means they are square matrices, right? So the order of Q and P should be m by m and n by n. Okay, so and if this relation is satisfied, B equal to QAP, then we say that A and B are equivalent. Okay, so this is the abstract definition we have for equivalence of matrices. Now, where does this equivalence relation come? Okay, so let's see that. Let us consider the set of all m by n matrices. So here this set A is nothing but the set of all m by n matrices. Okay, with entries from R. So we are having real entries. Equivalence of matrices on m by n of R is an equivalence relation. What does it mean? You take any matrix, A is equivalent to itself. How? So if A is equivalent to itself, what is that we need to show? We should be able to find a Q and P such that A is equal to QAP. What can be the Q and what can be the P so that A is equal to QAP? We have the obvious choices. What are the obvious choices? We can take Q is the identity matrix of order M and P is the identity matrix of order N. In that case, what to get? You will get if you put identity here and identity here, will this equation get satisfied? Yeah. So
Yes.
do you see that A is equivalent to itself? Yeah. So the first thing we saw is that, so this relationship here, we understood that it is reflexive because this condition satisfies where Q is this and P is this. Okay. The next thing is that we want to say that if A is equivalent to B, then B is equivalent to A. We want to prove symmetric. Okay. So first we will assume A is symmetric to B. So if A is equivalent to B, if A is equivalent to B, then what do we know? We know that we have two matrices P and Q of order n and m respectively, such that B equal to QAP. Right? So these P and Q are invertible. Right? So since they are invertible, what can we do? Let's do the following. Okay, so I am going to just multiply Q inverse here on
Excuse
both.
me, ma'am.
Yes,
Ma'am, in starting you say the order of P and Q should be same. And now you are saying the in this going on line you are saying P and Q order should be N and M, kind of a square matrix. Is
I guess you
this
got no, I get you got confused. I said order of A and B should be same, not P and Q. A and B should have the same order, not P and Q. Okay?
okay, ma'am? Thank you.
Okay. So now what are we doing? We are pre-multiplying with B and pre-multiplying with Q inverse and post-multiplying with P inverse. So we are having something like this. So now if you pair up these terms, Q inverse Q and PP inverse, what is Q inverse Q?
I identity
I
matrix.
Identity matrix.
And PP inverse is?
I
Again identity matrix.
I
Yes. So you get this is IM again and this is IN again. So this is A. So you get Q inverse BP inverse is equal to A. Right? So it means what? Here I'm able to have A as Q inverse BP inverse. So now this is my, let's rewrite this. So I have invertible matrices Q dash and P dash, where Q dash is nothing but Q inverse and P dash is nothing but P inverse, such that A equal to Q dash B P inverse. So P dash. So this means that again B is similar to A, B is equivalent to A. So first we assumed A is equivalent to B, because of which we had this. Now I'm having this expression. From this expression, I know that these are invertible matrices and this expression tells me that B is equivalent to A. Is that clear?
Yes, ma'am.
Yeah. Okay. Fine. Okay. So we are done with symmetric. What is the next part? What is the next part?
Transitive.
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 So for transitiveness, what is that we need to do? We assume,
If A comma B in the set and B comma C in the set, then A comma C should be also be present in the set.
yeah. So if A is equivalent to B and B is equivalent to C, then A should be equivalent to C. Yeah. So this is what we have for transitive. So now if A is equivalent to B, right, then we can have matrices Q and P satisfying this. And if B is equivalent to C, so this part implies this and this part implies this, where all this Q, P, Q dash, P dash, all of them are invertible matrices. Okay. Now, what do we want to prove? We want to have something like this. We want to have something like this. So let's say, so we want some Q tilde, A, P tilde. Okay. So this Q tilde and P tilde, we want invertible matrices. Okay. We want to find Q tilde and P tilde invertible matrices satisfying this condition. How are we going to achieve this? So for this B, I am first going to substitute this B here. Okay. If I substitute that, what will I get? I have C is equal to Q dash B P dash. Now instead of B, I am going to substitute this Q. So Q A P P dash. Now I am going to call this Q tilde is my Q dash Q and P tilde is PP dash. Okay. So now you see that Q tilde and P tilde, we need to say they are invertible. How can we say that they are invertible? So for a matrix, how do you know first of all whether a matrix is invertible or not?
We find determinant.
It
If
must be
determinant,
non-zero,
Matrices.
ma'am.
Okay. So now what is the determinant of this Q tilde? Is it non-zero or not?
non-zero determinant.
Yes, because say determinant of Q tilde, what do we know is determinant of Q dash into determinant of Q. And since both of them are already invertible, these are invertible, and hence we know that this is non-zero. Okay. And similarly, you can see that determinant of P tilde is determinant of P dash into determinant of P, and these two are again invertible, and hence this is also non-zero. Okay, and hence both of them are invertible matrices, and so now we have this kind of an expression where C equal to Q tilde A P tilde, and hence we can say that A is equivalent to C. Is this clear? Yeah. Okay. So till this point, is everything clear to everyone? Yeah. Shall we proceed? Okay. Now we will
Yes,
see
ma'am.
some examples here. Okay. So show that two matrices A and B are equivalent. Everyone, please take your paper and pen. Just you need to do some calculations and check what is the answer. So you are already given what is Q and P. Okay, they're very straightforward calculations, very simple calculations only. So easily you can do. Check this and tell me. So what is that you need to check? So to show that A and B are equivalent, what is that you need to check? Can you say?
A is
You need
equals
to
to
check
Q B B P.
B is equal to
Q A P.
AP. Okay, so can everyone check this one quickly? So here, in fact, what is your Q? Your Q is simply identity, and P is 0, 1, 0, 1, 0. Okay, so your calculation has even reduced to simply A times of this matrix. So just you can complete A into P and check till the answer.
Ma'am,
Ma'am, is this week
Yes.
seven content?
Yes.
ma'am,
Yes.
ma'am, what if in the question the Q and P are not given?
If they are not given, that is going to be very, very difficult to compute. Okay, so in exam, you won't be asked to compute Q and P. So don't worry about that. So usually your Q and P are given, or you will be given some hints where you will be having sufficient hints to compute Q and P. So directly just with the matrices asking Q and P, maybe suppose for example, if you have some case like this, where you have a trivial case, A is equivalent to A, you can find Q and P, right? Or some other cases where you have some specific logic behind how to find this, maybe something like this. Not directly, but we also have given the procedure to find Q and P. Okay, so I have added that procedure also later on. I will explain it. But usually such questions to compute completely Q and P is very, very rare. Okay, fine. But
Okay,
if you
ma'am.
want, definitely you have the procedure with you to see. All right. So did you check whether
Yes,
inequality
ma'am,
is obeyed?
equal.
Yeah, they are
Checked it.
equal, right? Okay. Good. All right. So now here is one
Ma'am,
important. Yes.
I is the order of 3 cross 3, right?
Yeah.
Or what, ma'am?
This is a 3 by 3 identity matrix. Okay. Fine. So as I told you, finding P and Q is mostly difficult. Okay. Fine. Now here you
Ma'am,
are given A. Yes.
ma'am, you are saying identity matrix is of 3 by 3.
Yeah.
P. P is 2 cross 2, na?
I did not say P is 2 cross 2. I'm talking about Q is I. Oh, the student asked whether P is
Okay, okay.
identity. So Q is identity, P is this matrix. This is not identity. No.
Yes,
Okay.
I maybe got wrong.
Okay, fine. So now we are having two matrices A and B. Can you say what is the size of these two matrices?
3 cross 2 cross 3
2 plus
for
3.
both.
2 cross 3, right? So now these two are equivalent. So this means that we will be able to find Q and P such that this condition is satisfied. So this is 2 cross 3. So this is 2 cross 3. And we are given Q, which is 2 cross 2. So what should be the order of P? Can you tell? P should be of order
And rows
2
must
cross
start with
3.
3.
2 cross 3.
3 cross 2.
3
Ma'am, 3
cross
plus
2.
3.
3
Yeah.
cross 3.
2 cross 3.
At the end, it
Take
should be 2 plus 3.
3 cross 3.
here it is 3, so here also it should be 3. And here it's 3, so here also it should be 3. Right? Okay. So this should be a 3 cross 3 matrix. Now we are asked to find the number of possible choices for P. Okay. So we don't know what is this matrix P. So what are we going to do? We are just going to have P as, let P is equal to, everyone take your paper and pen. We are going to do some matrix multiplication. A, B, C, D, E, F, G, H, I. Okay. So we are going to see what are the possible choices for this P. Okay. Now, what is that you are given with? You are given with B is equal to, which is 1 minus 1, 0, 1, 2, 1, equal to Q times of, what is Q? Your Q is 0, 1, 1, 0 times of A. What is your A? 1 minus 1, 0, 0, 1, 1 times of T. So your P is A, B, C, D, E, F, G, H, I. Okay. Can you compute this and do the matrix multiplication and tell me the resulting matrix? What is the first row? What is the first row here?
A plus
0
2D plus
1
D.
1.
0, 1, 1. Okay. What's the second row?
1 minus 1, 0.
1 minus 1 0.
Good. Okay. So let's do the next step of matrix multiplication. Do the next matrix multiplication as well.
Ma'am, actually, P is
Yeah.
3 cross 3. Just wanted to
Sorry,
ask
what?
as
Yeah, what's your question?
nothing, ma'am.
Okay. So what is the first row again?
D plus F, D plus G, E plus H,
F plus
E.
I,
A,
yeah.
uh,
And then second row start with A minus D,
B minus E,
One
and
minute.
C minus F.
Good. Okay. Now you have to compute coordinate wise for each of this term. So what are the equations you are having? D plus G is equal to 1. E plus H equal to minus 1. F plus I equal to 0. And then A minus D equal to 1. B minus E equal to 2. And then C minus F is equal to 1. Okay. Fine. Now let's do step by step. So from here, D plus G equal to 1 implies G is equal to 1 minus D. And I can write H as H is equal to minus 1 minus E. And then again I is equal to minus F, right? And then again you are having D in terms of A, right? So here maybe you can write D is equal to 1 or A minus 1. D is A minus 1. And what about E? E is, how can we write E? B
B
minus,
minus 2.
and then I can write F as C minus 1. So again, I can rewrite them. I can substitute this D value here. So G is equal to, what I can write in terms of D, in place of D, I can write 1 minus A plus 1, which is 2 minus A. And H is minus 1 minus B plus 2, which is 1 minus B. And I is minus C plus 1. Okay. So what is the original matrix P now? P, your first row is ABC. What is your second row? In place of D, what can I write? In place of D, E, F, what can I write?
A
B is
minus
A
1, B
minus
minus
1.
1, C minus 1.
B minus 2 and C
C
minus 1.
minus 1.
What about the last row? G, H, and I? 2
2
minus
minus
A.
A, 1 minus B, and 1 minus C.
Yeah. So these are the other entries. Okay. Fine. Now, what is the determinant of this matrix? We want this P to be invertible. We want P to be invertible. So what is the determinant of this matrix? Can you compute and tell me?
Must be non-zero.
Is zero?
0, because these are multiples of each other somewhere.
No, how do you know they are multiples of each other? No, I'm
No,
Uh,
no,
asking
not
compute
multiple.
the,
if we subtract second row and first, we get numbers directly.
okay, so if you think they are,
Maybe if we split the middle row.
uh, uh,
Two matrices.
There are so much of confusion. Before that, compute the determinant as a matrix. First, do that. Shall we? So A into B minus 2 into 1 minus C, and then minus 1 minus B into C minus 1. So in this way, if we compute, what is that we are getting?
Minus A minus B plus 3C.
Yeah, there is so much to still compute. Complete it and tell me the answer. What is the final answer you are getting? The simplified one? Did anyone calculate it?
I'm almost there.
Minus A minus B plus 3C.
Minus A minus B plus 3C. Yes.
Yeah.
How many of you got this answer? Okay.
Yes, ma'am, I'm getting the answer.
Okay, good. So, what are the possible choices of P? All such P where you have minus A minus B plus 3C is non-zero. Or maybe you can even rewrite it as A plus B is not equal to 3C. Something like this. Okay. So, under this condition, you know that this matrix is invertible. Okay. So, if you have this condition, this will guarantee you that P is invertible. Okay. So, now can you answer the question? Going back to the question, if it is given that Q is this matrix, then find the number of possible choices for P. How many choices can you find for this? What is your guess? How many matrices? So basically, you need to find ABC satisfying this condition and then just plug the ABC here. That's all. So how many such ABC do you think you can find?
Ma'am, one.
Only one?
No,
I
it's
think
unique
it would be
solution.
infinite.
Definitely it's infinite, right?
Yes, ma'am.
Yeah, infinitely many choices. Yeah. So the answer is, so we can choose ABC in infinitely many ways, and ABC satisfying this condition, and hence the number of choices for P is also infinite. Is this clear? Yeah. So your Q and P need not be unique. Okay. So for this Q, we had definite so many different choices of P.
Ma'am, this Q and P need not be unique in like every cases, or like few cases they are unique, few cases they are not unique.
Mostly it need not be unique.
Okay, ma'am.
Yeah. All right. Okay. So till this everything fine, right? So next we will move on to looking at the procedure, actual procedure to find P and Q. Because this is like, just imagine you are just given a small 2 by 3 matrix. You are also given one matrix Q and you are just asked to compute P. That involves so much of computation. If you are having a very big matrix, then finding Q and P, imagine if you have to compute both Q and P, how many equations you may have to solve. So we have a specific way of solving this. Okay. Consider, so now we are again going back to linear transformation here. That is another important thing we have to notice that. So in week 6, you might have seen matrices transformation of linear transformation with respect to various bases, right? So you take same basis for domain and codomain. Sometimes you take different basis for domain and different basis for codomain, right? So you have so many different representations for this linear transformation. So every time you are getting a different matrix, right? So what is that one thing you can check? Maybe I will take a small example here before moving on. So maybe let's do this small exercise quickly. So let's say T of x comma y is very simple transformation. Let's take y comma x. Okay. Now I want the matrix representation of T with respect to standard basis. So what is the matrix representation? Let's see. What is the matrix representation?
1 0 1 0.
0 1 1 0.
0, 1, 1, 0. Okay. So this is for standard basis for both domain and codomain. Suppose I want, let's say for domain, I want 1, 1, 1 minus 1, and for codomain standard basis. Then what's the matrix? So you need to find T of 1 comma 1 and T of 1 comma minus 1. What is T of 1 comma 1?
1 1
And 1 comma minus 1?
-1,
-1, 1.
So what should be the matrix? What is the first column? 1 1.
1 1 1 -1 1.
Okay. So you see that A1, A2 are two different matrices representing the same transformation. Now, what is the link between A and A2? Are there any is there anything which is common for A1 and A2? That's what we are going to see now. Okay. So here, consider a linear transformation T from V to W. Okay. Let beta 1 here is the set of all vectors v1, v2, vn, and beta 2 is the set of all vectors u1, u2, un. Now these are two ordered bases of V. Now gamma 1 is W1, W2, Wm, and gamma 2 is X1, X2, Xm. Now these are again another set of ordered bases of W. Okay. So now you see that we are having two different bases for V itself and two different bases for W. Now A is the matrix representation of T with respect to beta 1 of V and gamma 1 of W. Okay, so how do you express it? What is the step? What are the steps needed here? So what is that we do first? We do
T of V1.
TV1, yeah, TV1, and then express it as a linear combination of
W1, W2.
exactly. So we have, let's say, for example, alpha 1 1 W1, alpha 2 1 W2, etc.
Ma'am,
Alpha
can you
n.
please repeat the step? What we have to do?
Okay, so here usually what is the way to do the matrix representation? You do T of, so suppose you want to express T with respect to basis beta 1 for domain and gamma 1 for codomain, then you have to first find TV1, TV2 and etc. up to TVN you have to find, and all these vectors you have to express them as a linear combination of the basis given for codomain. So here, for example, something like this. And for TV2, it should be T alpha 21, W1, alpha 22, W2, plus and so on, alpha N2, WN. Similar, alpha 2N here also. So it should be 1, 2 here also.
Ma'am, could you do this for the previous example?
Exactly, that is what we have done in the previous case, right? So we have done, for example, here is the B, what is the matrix? Beta 1, gamma 1. Okay. So in this case, beta 1 is, let's say, 1, 0, 0, 1. This is your V1, this is your V2. So your TV1 is 0 V1 plus 1 V2, right? What is TV1? TV1 is actually 0 comma 1, which is 0 times of 1 comma 0 plus 1 times of 0 comma 1. Similarly, what is TV2? It is 1 V1 plus 0 V2, because what is TV2? TV2 is 1 0. So it is 1 times of 1 comma 0 and 0 times of 0 comma 1. So 0 1 1 0. Similarly, here what is your basis? So your beta 2 is 1. So this is your beta 2, and here you have, this is the other basis. So what is that you have done? This is your TV1, TV2, and this I have expressed it as, so now, okay, maybe I should call this as W1, W2. So TW1, TW2 in terms of V1 and V2. So what is that? It is 1 V1 plus 1 V2, and here minus 1 V1 plus 1 V2. So 1 1 minus 1 1. Okay. Yes. Yes. What's your question?
Ma'am, I just wanted to ask, while taking the TV1 or any T vector, we take it horizontally of a matrix. But while writing the equation in the matrix form again, we take it uh, in the vertical form. Means
Exactly.
vertically we write.
Exactly.
It's a bit
Correct.
confusing. Could you please tell that once again? How?
See, here what are we doing? We are having, for example, here TV1 is this, TV2 is this, and TVN is 1N, W1, etc. Alpha 2N, W2 plus alpha NN, WN. Okay. So now for writing the matrix A, remember the first column are the entries of TV1. The second column are the entries of TV2. The last column up to TVN. Okay. So what are the
The
coefficients of
again forming the equations, we take them as columns itself, or we take the rows and then form the equations.
we are not doing any rows thing here. We are just calculating the coefficients of W1, W2, Wn. That's all. Here there is nothing like row or column involved here. Only when you are
So,
writing it in the matrix, you have to write the coefficients of TV1 as the first column. Okay.
yes,
So
I
the
understand
coefficients of
that, but I'm asking the vice versa. I'm
Mm,
asking if I have a matrix A with
mm,
some entries in it,
mm.
columns and entries in it. Then when we take the equations out of it, means when we make the equations out of that matrix, then we are taking from column, we are forming the equation, or by the rows we are forming the equation.
What do you mean by forming equation? What equation are you talking about?
T1.
So,
T1 is
are
the
you,
equation of alpha and beta, right? Addition of alpha and beta.
what? Addition of alpha and beta. What?
She's asking how can we form the linear transformation from the if the matrix is given.
Okay, so that I have actually explained in the last class itself. So once we have the matrix again, the process is exactly, it should be exactly same, right? So here you should take the first column is TV1, second column is TV2. Exactly, it should be the same. It cannot be different from that, right? So
Ma'am,
for
we
yeah,
have to express T1 as a linear combination of the basis vector of codomain. So is it
exactly.
important that the basis vector are standard basis vector?
See,
Can they be
as I told
different?
you in the yes, definitely it can be different. If you have attended the last session, you would have not asked this question. The last session, I have given example where we have tried different bases and I have done different matrix representation of a transformation. Please go and visit the last session. Okay. Fine.
Ma'am, if W1, W2, and Wn are not standard basis, then
Hmm.
finding the coefficient alpha 1 1 and other coefficients will be difficult. No?
Yes, it will be difficult. You have to solve some system of linear equation to get the coefficients. So each of this equation
Eh,
involves solving a system of linear equation.
In the previous example, you wrote by inspection the coefficients.
Oh, in this case, see, purposely I took the codomain as standard basis because once the codomain is standard basis, there is nothing to compute, right? Because once the codomain is standard basis, any vector, how do you express it as a linear combination of the standard basis?
Yes, ma'am. Yes, ma'am. I got it. This one, but if
Yeah,
standard basis are not there, then ma'am, how to
then
do?
it will involve some computations. You have to do some computations.
Okay.
Okay, so suppose this is your basis given. Suppose with respect to this basis. Okay, so in that case, you have to do some calculation. So suppose let's say this is beta 1 and beta 2, right? So suppose you have to find matrix of T with beta for domain, you take beta 1 and codomain, you take beta 2. Then it's going to be difficult. Not difficult, like involves more computation because you are going to find T of 1 0. What is T of 1 0? 0 1. But you have to find, write it as a linear combination of what is your V1? So here it is 1 1 and 1 minus 1. Okay, you have to express it in this way. So you have to find what are they. How will you find it? You have to again make some equations out of it. So alpha 1 1 plus alpha 2 1 is 0 and alpha 1 1 minus alpha 2 1 is 1. You solve the system of linear equation, you will get the coefficients. Okay?
Okay, ma'am. Thank you.
All right. Okay. So while going from matrix to transformation also, it's exactly the same process. Oh, sorry, here it's 1n, 2n, nn. Okay, so this is the matrix. Now I have already given you how to form the matrix A. Okay, so similarly, can you try? So maybe so the elements of beta 2 are ui's and elements of gamma 2 are xi's. So these are beta, ui's. So u1, u2, un, and this is gamma 2. x1, x2, xn. Now can you try it yourself how to do this? So maybe let's call the coefficient as beta ij in this case. So let's call the entries of B as beta ij. So how can we do this? Can you tell? What is the first step?
TU1.
T of U1
P
goes
of
to
U1,
beta 1 1, beta 1
beta 1.
1, x1 plus beta 1 2,
Remember, this is the first column, not the first row. So what should be this?
beta 2 1,
Yeah,
x2 up to beta n1 xn,
very good. Very good. What should be TU2?
beta 1 2, x1 beta 2 2 up to beta n2 xn.
Okay. So now TUN is beta
Beta
1
1 n
n,
x1
beta 2n x2 plus etc. Beta nn.
xn.
Okay. So our matrix B is all this beta 1 1, beta 1 2, etc. Beta 1 n. So this is your TU1, this is your TU2, this is your TUN, right? So here you should have beta 2 1 up to beta n1. Here you should have beta 2 2 up to beta n2, and here you should have beta 2n up to beta nn. Okay,
Ma'am, here we
so
are given the values of TU1, TU2, and TUN.
we are not given the values, that's why we are putting abstract coefficients here. Okay.
Then how will we find out, ma'am, beta 1 1? Because if
Yeah, if it
TU1,
is given, if it is given, then we can find. Here it is not given, so I am giving some variables for each of this, just some abstract values like b11, b21, just some variable I am using because I don't know what are the values of tu1, tu2. Once it is given, I know how to compute. Just like this, I have to form system of linear equations and then solve it.
okay, ma'am. Thank you.
Okay. Now, okay, so in this case, what is the relation between A and B? So the question was, under such a scenario, what is the relation between these matrices? Okay, so the relation is that A and B are equivalent. Okay, and it satisfies the equality P is equal to QAP, where P and Q are defined as follows. Okay, so I told you earlier that I will be giving the technique of finding P and Q specifically in such a scenario. Okay, this technique is not applicable in very common scenario where A and B are some matrices, but this is a specific case where A and B are defined in this way. Okay, now how do you find P and Q? Okay, for P, express the elements of the ordered basis beta 2 in terms of the ordered basis of beta 1. Okay, so how do you express the elements of the ordered basis beta 2 in terms of beta 1? All those coefficients, put them as the matrix that will give you P. Okay, fine. Similarly, express the elements of the ordered basis gamma 1 in terms of the ordered basis gamma 2. That will give you some coefficients that you put it as the matrix Q. Now, if you compute QAP, you will get back B, like magic. Okay, definitely it's not magic. So you have a specific logic. So once you complete, do the matrix multiplication, so you will get back this matrix B. Okay.
Can you just repeat what you just said, ma'am? The steps.
Yes.
Yes,
Yes.
ma'am.
Okay.
Overview will be better.
Yes, yes, I'll tell. Okay, so now what is that we are given? We are given that, so we are having a linear transformation T from V to W. Now A is the matrix representation of T. So with respect to beta 1 for the domain, am I correct? Beta 1 for the domain and gamma 1 for the codomain. Similarly, B is the matrix of T with respect to beta 2 for domain and gamma 2 for codomain. Now, what is the relation between these two matrices? They are equivalent. Now, we are going to find Q and P as follows. How are we going to find Q? Q is the matrix obtained from expressing gamma 1 in terms of gamma 2. So you have to express gamma 1 in terms of gamma 2. And how are we going to obtain P? We are going to express beta 2 in terms of beta 1. Okay. So if we are doing this, then we will get back B. BAP will be, QAP will be again B. Okay. So
Ma'am,
here,
ma'am, the Q matrix is from 1 to 2 and P matrix is from 2 to 1.
yes.
Okay, ma'am.
Okay.
Ma'am, if we express gamma 2 in terms of gamma 1 and beta 2 in terms of beta 1, then if we reverse,
No, if you reverse, you will get different matrices. See, if here some order is different, then you can do that. But here, because of this specific order, you have to follow this order here. See, maybe you can remember it something like this. So, here, I don't know exactly how to write. So, I'll try if I'm able to give you some way to remember. Please mute.
ma'am, excuse me, ma'am.
Yes,
Ma'am, can you please elaborate the line gamma 1 in terms of gamma 2 and
yes.
beta 2 in.
Yeah, I'll do that. Okay. So
Is
here
this
A,
is this
yes.
in general or there's some specifications to this?
Sorry, what?
Is this general case?
Yeah, so I have given all in terms of common symbols only, not any specific case, right? Okay. So here A is the matrix of T with respect to beta 1 for domain and gamma 1 for codomain. Okay. So now you have P here. Okay. So you are going to represent beta 2 in terms of beta 1 for P. And Q, what are you going to do for Q? For Q, it is gamma 1 in terms of gamma 2. Okay. So for P, you are having, so for P, it is beta 2 in terms of beta 1. So wherever you are leaving beta 1, so it is ending with beta 1 again for P. And here for B, you are like having gamma 2 here. And similarly, here you are having gamma 2 for Q. Something like this you can remember. Okay. I don't know exactly in what way you will remember, but there is a logic behind this. If you do some problems, you will have a better understanding. Okay, so let me explain what it means by gamma 1 in terms of gamma 2 and beta 2 in terms of beta 1 and all that with this example. Okay, we will do a specific example, then all your doubts will be clear, I guess. You will have a very clear understanding if we do this example. Shall we? Okay,
Yes,
everyone.
ma'am.
Take your paper
Yes,
and pen. Get ready for the adventure. Okay, let's try. Very simple example. So first step, we are going to find the matrix A and B. Okay. So first step to find matrix A and B. Here we are going to first find it with respect to beta 1 for domain and gamma 1 for codomain. So this is your beta 1. So this is a specific scenario we are considering. Beta 1 is the standard basis, gamma 1 is also the standard basis. So this is the easiest case we are considering. Okay, so what should be A? So you find, let's call this B1, B2, B3, W1 and W2. So what is TV1? So your T is here. What is TV1? Yeah. What is TV1? What is T of 1, 0, 0? Substitute and tell me. It's not a big deal.
1 multiplied by W1.
1 minus 1.
Okay.
1 and
1.
minus.
So it is 1 W1 minus 1 W2. Right? Because it is standard basis, it's straightforward. Again, what is TV2? Yeah.
0, comma 2.
Okay. 1
1,
comma 2 is
0, 1, comma 0.
sorry, what?
Sorry, I just done for V3.
Okay.
Skip V2.
V2 is 1, comma 0.
V3 is again 0 comma. Okay.
2. 0, comma 2.
Okay, fine. I also did not check. So this is 1 comma 0 and this is 0 comma 2. Correct. So 1W1 plus 0W2, 0W1 plus 2W2. Okay, fine. So what is your matrix A?
1 minus 1.
Yes.
1 minus 1. 1, 0 and 0, 2.
Yes, someone is asking some doubts, I guess. Yes, ask me.
Yes, ma'am. How this 1 comma minus 1, 1 comma 0, and 0 comma 2 came?
Because we are following the
Transformation, ma'am.
yes. Oh, it's given as x1, x2, x3. Yeah, I'm just substituting x1, x2, x3 in place of x1, x2, x3. If I substitute 1, 0, 0, what will I get? I'm checking that and writing. That's all.
Okay, ma'am.
Got it? Okay. Fine. Okay. So now we have the matrix A. A is the easiest one. So next we'll find what is B. So for finding B, you have what was the name for the other one? I forgot. So it was okay, U1 and X1. Okay. So this is your U1, U2, U3. This is your X1 and X2. So you have to find TU1, TU2, TU3. Find what is TU1.
1 comma minus 3.
1 comma minus
Minus
3. Minus 2, minus 1, minus 3. Yes. And what is TU2?
2 comma 1.
2 comma 1. Okay. So you have 1, 1, 1. So 2. Yeah. What is TU3?
1 comma minus
1,
1.
comma minus 1.
Now you have to express each of this as a coefficient in terms of x1 and x2. So here you have coefficients.
1, 1
So
comma 0.
beta 1, 1. So what are the coefficients you need to find in each of this case? So can you find and tell me the coefficients?
1. It will be 1.
This is 1.
Ma'am,
Yes, ma'am.
Minus 3 or
1 and
1.
minus 3.
Yes. And here
Minus 3. 2, 1.
1, comma 2. 1 and 2.
and minus 1 and 1.
Yeah. So here, what is your B?
1 minus 3.
Minus
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 1, 1, 2, minus 1, 1. You have to write the coefficients of x1 and x2. Okay, not the vectors as it is. Writing the coefficients of x1 and x2 here. So we have got the matrix A, matrix P. Next, for matrix P and Q, what is that we need to do? For matrix P, what is that we need to do? And matrix Q, what is that we need to do?
For Q, express gamma 1 in terms of gamma 2.
Yes, gamma 1 in
For,
terms of
for P, beta 2 in terms of beta 1.
beta 2 in terms of beta 1. Okay, let's try that. So here, what is your beta 2? This is your beta 2. So this is also very easy. Beta 2 in terms of beta 1. So here, what is your beta 2? Yes.
Ma'am, in
Ask
the
it.
previous step, why have you multiplied the codomains here? Like for T, U1, T, U2. That part alone is confusing. I can understand the minus 3 and all. It's part of the linear transformation, but why is there a 0, comma 1 and 1, comma 0? Why we didn't do the same step for the previous one, right?
Yes,
Here,
ma'am.
Yeah,
this
yes, ma'am.
this
We
part
didn't.
you're
No, not that one, ma'am. The T U1 and T U2, right? We have multiplied the codomain values, like the codomain vectors.
yes.
I just want to know why.
That is the way you do the matrix representation, right? How do you do the matrix representation?
No, ma'am, I think he's asking right. At first, you write 1 W1 and minus 1 W, and in the during U1, you just reverse it minus 3 U2 and 1 U1.
Reversed it, ma'am. So
Yes, because the vectors are also reversed, right? Because here you see this is your x1, this is your x2. So what is the coefficient of x1? The coefficient of x1 is minus 3 here. The coefficient of x2 is 1 here. Because the vectors are, these are ordered bases. Remember, they are ordered. You cannot change the order of the bases given. Okay? Did I answer your question?
Yes, ma'am, got it.
Okay, the other guy?
Ma'am, if we change the order, then also it will not matter.
Yes, ma'am.
If you change the order, then you are finding a different matrix. Okay? Not this matrix.
Same coefficients will come, ma'am.
No. If you are changing, having a different basis, the same coefficients need not come. All right. So moving on. So here we will complete this part. Beta 2 in terms of beta 1. So what are the vectors in beta 2? So in beta 2, we had 1, 0, minus 1, 1, 1, 1, and 1, 0, 0. So these are your U1, U2, U3. Now I want to express U1 as a linear combination of the elements of beta 1. What are the elements of beta 1? B1. So V1, V2, V3. What are the coefficients? Very straightforward because V1, V2, V3 are standard bases. Can you tell what are the coefficients?
1 0 minus 1.
Similarly, for U2,
Ma'am, 1 1 1.
for U3,
1
1.
0 0.
Yeah. So what should be your matrix P?
1 0 minus 1. 1 1 1 and 1 0 0.
Okay. Now the next step is we have gamma 1 in terms of gamma 2. So what is gamma 1? Gamma 1 is 1 0 0 1 and gamma 2 is 0 1 1 0. Right? So you have this is W1 W2, this is X1 X2. You want to write W1 in terms of X1 X2. So what are the coefficients of X1 X2 in terms of W1?
Ma'am, 0, 1.
0, 1. Okay. And for
And
W2,
1, 0.
1-0.
that's all. Very easy example, right? So now,
Ma'am,
yes.
ma'am, if I do like for P, if I do B1 in terms of B2, and for Q, if I do B
You will get the
gamma
wrong
2 in terms
answer.
of gamma 1, then the position of A and B will get interchanged now.
Position of A and B will interchange. That you have to verify, check and verify. I guess it will, yeah, I guess it will be working in that way. It's supposed to, most probably should be interchanged like this. Okay.
Okay, ma'am. Okay.
Ma'am, how to remember which base in terms of which? Because beta 1, beta 2 by symbol we
Yes,
say
ma'am. We can write even beta 1 in as beta 2 in questions
the
too.
mistake may be committed, ma'am.
It is only a symbol like.
I don't know exactly some. Is there any technique to remember? I don't know. So here you have B, B for domain. What is it you have for B? For B, what is it you have for domain?
Beta 2.
Beta 2. Okay. And for codomain,
Gamma 2.
gamma 2. And then you have B equal to Q, right? So for Q, you have gamma 1 in terms of gamma 2. And then A, you have, for A, what is that you have? Beta 1 in terms, beta 1 for domain and gamma 1 for codomain. And then for P, you have beta 2 in terms of beta 1, right? I don't know what kind of a relationship you are having here. Is there any relationship? I don't know. Something like this. I don't. It will work only for this case, and here you have this and this. Okay. I don't know. See whether you have any specific technique or something like this to remember. Okay, I don't know. Any shortcut to remember, but yeah, this is how it will work.
Ma'am, this is how they
Okay.
raise the questions in the exam, right? Like find out these matrices like this.
That's what I told you in the very beginning. So you will not be specifically asked to find P and Q
P and Q. Hmm.
explicitly. That's very, very rare.
Okay,
Okay.
ma'am.
So, but this is the technique, and you should know the technique. In case of some very simple examples, maybe you should know the technique. Okay. So here you have. So I'm not going to do the matrix multiplication and do the verification. So the verification process, I leave it to you.
Okay, ma'am.
Input equal to QAP, verify this. Okay, fine.
Okay, ma'am.
All right. So
And what to verify? B is equal to
you do QAP, you do the matrix multiplication QAP,
okay.
and you are getting back B.
B, okay.
Yeah. Okay. So now, so far we have seen what are equivalent matrices. Okay. How to get the Q and P in some specific case, right? And now we are going to look at some important characterization of equivalent matrices. Like given two matrices, how to check whether they are equivalent or not. Very easy. So first, what is the very first condition? They should be of same order. The matrices should be of same order. Remember, A and B should be of same order. That is the first thing you should see. Okay. Next, what is that you can see? Whether A can be transformed into B by a combination of elementary row or column operation. Okay. So whether you can obtain B from A by doing some row or column operations. Or even easier, or A and B are equivalent if rank of A equal to rank of B. Just verify the rank, then you know whether they are equivalent or not. You just have to find the rank of the matrices. Okay, if they are equal, then you know that they are equivalent. Now look at these two matrices. First of all, are they of same order?
Yes, ma'am.
Okay. Now consider these two rows. These two rows, are they linearly independent?
No, ma'am.
They are linearly independent because you have a minus here, right? They are linearly independent only, right? One is not a multiple of the other, right?
Yes, ma'am.
Yes, ma'am.
Yes.
Yeah. So what is rank of A?
2.
2.
2.
Similarly, what about P? Are they linearly independent, the rows?
Yes, ma'am.
Yes, ma'am.
So in that case, what should be the rank of P?
3.
2.
Sorry,
2.
2. 2.
You see that rank of A equal to rank of B. So this implies A and B are equivalent.
Ma'am, after calculating the REF form, we will get the rank, or means we have to calculate by that method, or by direct seeing any matrix we can tell.
Calculating rank is completely up to you. You can use any method you want. Okay? Fine.
Okay, ma'am.
So check whether these two matrices are equivalent. Are these two matrices equivalent? You should answer just straight away. Look at the matrix and say the
No,
answer.
No.
ma'am, order is not same.
Yeah.
Order is not same. Rank is not same.
So first you should see this. Okay. Fine. Now we'll see these matrices. What about these matrices? Are they equivalent? You have to look at the rank of these matrices. Okay. So there is one shortcut here. Now for this matrix, do you know what is the determinant? What is the, you see
Minus 3.
Minus 6.
Minus 6.
Minus
Minus
6, ma'am.
minus.
Minus 6. Sorry.
What is the determinant of this matrix? So if this determinant is non-zero, what do you know about the rank?
Lesser than dimension, ma'am.
Rank is full.
Yeah, it's
3.
full matrix.
Rank is full.
Yeah. Now what is the determinant of this matrix? Calculate and tell me.
Rank is 2 because 2 into 3 into first row plus second row gives.
Yeah. So either you can look at the linear population or you can see the determinant is 0. So you know that rank is strictly less than 3. So rank of A is not equal to rank of B.
Ma'am, how can we conclude that if determinant is non-zero, then rank is full?
If determinant is non-zero, why rank is full?
Yes, ma'am.
Go back to week 1 and 2 videos and see. I don't have time to explain it here. Okay. Fine. So this implies A and B are not equivalent. I guess specifically I myself have discussed this part at the end of week 4 maybe. I'm not sure exactly when, but I guess in week 4 discussed, I
While
guess.
revising week 3 and 4, you have told about rank.
Yes. If A and B are equivalent matrices of order m by n, indicate whether the following are true. A transpose and B transpose are equivalent. First of all, A and B are equivalent. So if A and B are equivalent, what do we know? We know B equal to Q, A, B, where Q
2A.
and B invertible matrices. Okay. Now we are asked to check whether the following are true. A transpose and B transpose are equivalent. Is it true?
Yes, ma'am. Because
Okay.
rank doesn't change on taking turns.
Yes, yes, very good argument. So the rank will not change. Okay. Can you find Q and P in that case?
Ma'am, we can take transpose of B is equal to QAP equation on both sides.
Exactly. So for first one, you simply take the transpose on both sides. What happens when you take transpose of product? It gets reversed, right? So you have this. Now you know that this is your Q dash and this is your P dash. And you know that they are invertible. So you can see that B transpose and A transpose are equivalent. Okay. First one, is it fine for everyone?
Yes, ma'am.
Okay. What about second one? A square and B square, are they equivalent? What is your guess? Will the rank of A and B, if they are same, can you guarantee that rank of A square and B square will also be same?
No, ma'am.
Okay. In that case, you have to give a counter example. I will give you A, you guess B. Okay, I will give you A. So if I give A, you can easily fill B. What is A square? What is rank of A first of all?
1.
1.
Okay. What is B square?
And 0, 0, 0.
All 0, 0.
So what is the rank in this case?
0.
0.
0.
Okay. Now give an example of a B such that A square and B square are not equivalent.
The identity matrix, maybe.
For identity matrix, A and B should be equivalent, right? So maybe in identity we can make one entry as
One
0.
is
Now what,
identity and other is some else matrix.
what about the B? Now you see that both these are same. So you know that A and B are equivalent. So rank of A is same as rank of B. So A and B are equivalent, right? Now what is B square?
0.
Equal to B only.
0 matrix.
And
It
rank
is B square is 1000, right? Yeah. So in this case, what is rank of B square?
1.
1. Right? So now you see that rank of A square and rank of B square are different. So you can say that A and B, are they equivalent or not?
Not
no.
equal.
Definitely
No.
No, ma'am.
not equal. So this statement here is false. What do you think about AB and BA? Okay, what is AB in this case? A into B? This is 0. This
0,
is
0,
1.
1, 0.
Okay, what is BA? 1, 0. Am I correct?
Yes,
Yes,
ma'am.
ma'am.
So what is rank of AB?
1.
1.
What is rank of
0.
BA? Okay, so you see that they are not equal and hence AB and BA are
Not equivalent.
not equal.
Excuse me, ma'am. For first example, A transpose and B transpose, uh, that P transpose, A transpose, that's okay. We are representing P transpose and Q transpose with Q dash and P dash.
Yes,
By this, what's the next? How can we conclude that they are equivalent?
they are.
equivalent. How are we
Because
confused?
we are, because from here what do we see? B transpose is equal to Q dash A transpose P dash. So if you have Q and P satisfying this condition, then P transpose is equivalent to A transpose, right? This is the definition.
Okay. Oh, okay, ma'am. Just we are representing P transpose and Q transpose as Q dash and P dash.
Yes, yes.
Okay.
Okay, clear?
Yes,
All
ma'am.
right. Okay. So regarding equivalent matrices, right? What are the things we have seen? So we say A is equivalent to B if you have B equal to QAP, where Q and P are invertible. And in terms of linear transformation, if you have T from V to W and you have two bases, beta 1, beta 2, gamma 1, gamma 2, and you have the matrix of B, A is this matrix and B is this matrix, and then you know that you have B is equal to QAP, right? Where what is Q and what is P? Q is, can someone complete? Let's see how many of you remember.
Gamma 1 in terms of gamma 2.
M M cross.
Q is gamma 1 in terms of gamma 2. Is that correct?
Yes, ma'am.
Yes, ma'am.
Okay. What about P?
Beta
Beta 2 in terms
Beta
of
2
gamma 1.
in terms of beta 1.
Okay. So this is what we have seen so far, right? And the other thing, important observation is that rank of A equal to rank of B. Okay, so these are the things we have seen so far about equivalent matrices. Only this much for 1 hour 45 minutes. Okay, fine, no problem. We will complete what are similar matrices next. Okay, so two matrices A and B of order n by n are said to be similar if there exists an invertible matrix P such that B equal to P inverse AP. We are now simplifying it even better. So equivalent matrices, we had Q. Now for similar matrices, instead of some random Q, it's just P inverse. Okay, if you have P inverse in place of Q, then we call A and B as similar. And another important thing you need to observe, notice is that here this is only applicable for square matrices. I am putting it in red because this is very important for similar. You cannot talk about similar matrices for rectangular matrices because here you see P inverse, it means the matrices are of same order. We are talking about square matrices here. Okay, so we check similarity only for square matrices. Okay, of same order, of course.
Ma'am,
Okay,
can we say that equivalent metrics of same order are similar?
no.
Okay, ma'am.
Okay, fine. So now verify similarity defines an equivalence relation. It's very straightforward, exactly the same technique as earlier. So A is similar to A because you can take P to be the identity matrix. Because what is I inverse?
I only.
P inverse is I again. So you know that A equal to P inverse AP. And A is equivalent to B implies or similar. Here we have similarity. So A is similar to B implies B is similar to A. Okay. So in this means what you have first B equal to P inverse AP. So again you apply the inverse technique. So if you apply inverse technique, what will you get? Okay, I'm not doing inverse here. Sorry. So I have to pre and post multiply. So P B P inverse equal to P inverse A P inverse. So this is identity. This is identity. So it is again A. So we get P is similar to A. Okay, and for the last scenario, A similar to B, B similar to C implies A is similar to C. Okay, again the exact same technique, nothing new. So if A is similar to B, you know that B equal to, let's say, P1 inverse AP1, and this implies C is equal to P2 inverse B P2. This implies C is equal to P2 inverse. Now I'm going to put this here. So P1 inverse AP1 P2. Okay. Now what is P1 P2 inverse? Can you say? Whole inverse. What is this? Can anyone say?
It is a invertible matrix, na ma'am?
And P2 inverse into P1 inverse.
Exactly. So it is P2 inverse into P1 inverse. So what is that we observe? So if I'm calling this as P, then this is nothing but P inverse. So what I have got, C is equal to P inverse AP. So this means I get that A is similar to C. So you see that this is also an equivalence relation. Okay. So reflexive, symmetric, and transitive. Okay. All the three things I have proved. Okay. So if two matrices are similar, then they are also equivalent. Agreed? Very easily see, right? This is your Q. So you see that obviously this is true. What about the converse? What about the converse? If two matrices are equivalent, can we say they are similar?
No, ma'am.
No.
Definitely not, right? Because
Square then.
It
yeah,
cannot be a square matrix.
exactly. Okay, even if it is square, we cannot say. Okay, for example, consider these two matrices. Are they equivalent? See, this is an important.
No.
Yes, ma'am.
No, ma'am.
Yes,
Rank of
ma'am.
same.
They are equivalent.
Okay, so rank of A is
No, ma'am, but
2.
A is
Two.
not equal to B, ma'am.
Two.
Rank of B is also 2. Okay, so rank of A is 2, rank of B is 2. So this implies A and B are equivalent. Now question is that can A and B be similar? We don't know whether they are similar. So what can we do? What can we do? Suppose A and B are similar. Suppose A and B are similar, then what happens? What is the definition?
There should be
And
one.
B is equal to
Mm.
P inverse
A.
A into P.
So now B inverse. Now what is your B? No, sorry, A. A is your identity matrix. Note that A is your identity matrix. So what will you get here on the RHS?
Identity matrix.
P inverse P.
P inverse P, which is again.
Identity matrix.
So are we getting a contradiction?
Yeah.
Yes, ma'am.
Okay. So this means that this assumption is wrong. Yeah, let me complete this statement and answer your question. So A and B are not similar. So this means what? This means that equivalence does not imply similarity even for square matrices. Got it? We have two square matrices which are equivalent, but we clearly see that they are not similar. Okay, fine. Yes. What's your question?
Ma'am, I also want to ask any equivalence. We only check the rank,
Yeah.
not the matrices particularly, right? And
Yes.
any similarity, we check the by its formula, right?
Yeah.
Okay, fine. Ma'am.
Yeah. Okay. So now we are going to see some examples. Now can you check whether these matrices are similar or not? Can they be similar? What is that you immediately observe? First of all,
Square
are
matrix.
their rank? Are their ranks same?
No, ma'am.
Rank is
So
same.
rank of A
Two.
is 2, rank of B is
One.
1.
1. So they are not equivalent. So here again, remember, not equivalent implies not similar. Okay, so equivalence does not imply similarity, but not equivalence implies not similar. Okay, so hence we have these two are not similar. Oh, so if A or B is invertible, then AB is similar to BA. What is that you think?
No, ma'am, they are not equivalent, so they cannot be similar.
Okay, so if A or B is here, we are talking about under some specific condition, not in general. So here you see that first one, let's suppose assume that A is invertible. Okay, now what can we say? So we have to find some matrix such that AB and BA are similar, right? So what can we do? What can we do? Any idea? Any guess?
We can write AB equal A inverse B.
Okay. So here the hint is choose P is equal to A. Now what happens to P inverse B A times of or A B times of P? What is your P inverse? You know already A is invertible. So what is P inverse? It is A inverse A B times of A. What is A inverse A?
Identity.
One identity matrix.
So it is simply so P inverse AB B is equal to BA. So can we say AB and BA are similar?
Yes, ma'am.
Okay, fine. Similarly, if B is invertible, then what is that you need to choose? If B is invertible, what is that you need to choose for P? Guess.
And P equal to B.
Then B.
Will B work? Check. What is the B? It's
B inverse. B
yes,
or
we
B
have
inverse.
two answers. You can try both and see which one works. Okay. So here it's about A power n, B power n. So now we are having A and B are similar. Can we have A power n and B power n similar? So if A and B are similar, then what do we know? We know that B equal to P inverse A. So now what is B square? P inverse A, P times of P inverse A. So this means P inverse A, P inverse AB. Now what is P inverse? Identity.
Fine.
So this means that this is nothing but a square p. Okay. So we see that b square equal to p inverse a square p. So similarly, we can obtain for any n, right? B power n equal to p inverse a power n p for any n. So you see that this is true. What about the third one? Again, the same technique we used like for the equivalent case. Okay. So try the same technique here also, it will work. A similar to B implies P equal to P inverse AP. And this implies B transpose equal to P inverse AP whole transpose. So what is P inverse transpose? The same as P transpose inverse. Hence, we can replace it with this. Okay. So here A transpose and B transpose are similar. Sorry, I missed the transpose here. Okay. Fine. So the procedure for finding P and Q is very much similar. Only thing you should be very careful is that for the similar matrix case, we are using the same basis for both domain and codomain. We are not having different bases. Okay. So similarity is possible only we are having same basis for both domain and codomain. Okay. So in that case, so again for P you have to express gamma in terms of beta, and for Q you have to express or P inverse you have to express beta in terms of.
Excuse me, ma'am.
Yes.
Ma'am, the line on which you focus on and underline the same basis and domain, I didn't get that point.
So this means that here you are having, for example, here. Okay, I don't have written here. So it means that, so here beta is V1, V2, Vn. So I have to express T V1 in terms of V1, V2, Vn. I'm not going to use any other basis.
Okay, like for the B, you are going to use U1, U2, UN.
Yeah.
Okay, ma'am.
Okay, fine. Okay. So now this is for similar matrices. Now here I have an example. I recommend you all to try it yourself. Is this doable? What do you think? Can you all try it yourself? This one?
Yes, ma'am.
Okay, try it yourself. Okay. So I will quickly do some properties alone and then we can wind up the session. Okay.
Ma'am, can you show
So
that question once again? That homework one?
okay,
Yes, thank you, ma'am.
fine. So if two matrices A and B are similar, then they have same rank, just like we had the property for equivalent matrices, right? So in fact, we can show that similarity implies equivalence, right? Similarity implies equivalence, and hence this implies same rank, right? So from this, we can say this. And then what? If two matrices A and B are similar, they also have the same trace. Okay. What is mean by trace of a matrix? Do you remember?
Ma'am, sum of diagonal elements.
Sum of diagonal elements.
Sum of diagonal elements. Okay. So here, if A and B are similar, you know that B equal to P inverse AP. Right? Now, what is trace of B? Trace of B is trace of P inverse AP. Now, what is that you know about trace? Trace of, let's say, if you have AB, it is same as trace of P. If you are using this property here, If you are using this property here, then let's rearrange and write. Then I can write it as trace of, I'm going to interchange these two alone. So I'm going to have A times of P inverse. Okay. So maybe, or I can have AP here and P inverse on the other side. That will make sense. So AP and P inverse interchanged. Okay, now what is P inverse is identity. So this is nothing but trace of P. So trace of P is same as trace of A. Okay. And if two matrices are similar, then they have the same determinant. I guess in determinant property, we have already seen
Excuse me,
what is the determinant of P inverse AP. Yes.
ma'am, can you please explain the trace alone one more time?
Yes. So here, you see, if you have trace of AB, it is same as trace of BA.
That
Now,
is
maybe
general rule, or as they are
yes,
similar.
no, it is a general rule. Maybe in place of A and B, let me put XY. Okay, XY, let's say they are two matrices, then this is applicable. Okay, now let's say that here you have X is equal to P inverse and Y is equal to AP. Now trace of XY is same as trace of YX, right? So now this is Y, this is X. Is that clear now?
Okay, ma'am. Yes, ma'am.
Okay. Now what is determinant of P inverse AP? Can anyone remember?
Determinant of P inverse multiplied by determinant of A multiplied by determinant of P.
Yeah. What is
Determinant of
determinant
A.
of? It is 1 by determinant of P, right?
Yes, ma'am.
Hence, you know that.
Determinant of A.
So determinant of P equal to this, because you have B equal to P inverse AP, you have. Okay, so you see that determinant of B and determinant of A are same. So you see that if their matrices are similar, then they have the same determinant. Is that clear? Yeah. So
Yes, ma'am.
similarity implies what are the properties? Similarity implies same
Same
rank.
rank, same trace, and same determinant.
Excuse me, ma'am.
Okay. So this is true. Yes. What's your question?
Ma'am, here the last in the last property you write determinant of P inverse AP equal determinant of P inverse into determinant of A and determinant of P. In this, how do you write determinant of P inverse equal 1 upon determinant of P? It is adjoint of P upon determinant of P, na?
It is a property of determinants. So I guess this was discussed in big two, I guess. Determinant of P
Maybe
inverse
I
and
forgot.
property of 1 by determinant of P. It's a formula. Okay, property. Can be obtained as a property of determinant also. Okay.
Okay, ma'am. My mistake. I forgot my.
Oh, okay, no problem. All right. If two matrices are similar, then they have same rank, trace, and determinant, but the converse is not true. Okay. So I already told that this is an important example. So for this matrices, we have already computed the rank, right? So we know that rank of A equal to rank of B equal to 2. Can you check the trace of A and trace of B?
Two,
What?
ma'am.
It's 2. Okay. What about the determinant of A and determinant of B?
1.
1, ma'am.
But what do we know about A and B?
They are equivalent.
They are not similar.
Not similar. Okay. So even though you have all these properties, this does not guarantee similarity. Okay. So similarity implies all this, but these properties do not imply similarity. Okay, so the converse is not true. Okay, fine. Okay, so here these two matrices, are they similar or not? How can we check? What is trace of A?
5,
What is trace of B?
4.
14. So they are not equal, hence they are not similar. What about these two matrices? Trace is same, but what is determinant?
6 and 4.
6 and 4.
Yes. So they are again not equal,
Not similar.
not similar. Okay, fine. So I guess we should stop here. Can a scalar matrix be similar to a non-scalar matrix? What is the answer you think?
No, I guess.
The trace could be different.
What do you mean by a scalar matrix? It is alpha times I. Okay, so let's say B is a non-scalar matrix. Suppose B is equal to P inverse A. What will happen? P inverse alpha I P. Alpha is just a number. So I can bring it out. It will reduce to alpha I. B is non-scalar, right? So this is not possible, correct? Hence, a scalar matrix cannot be similar to a non-scalar matrix. Is that clear? Yeah?
Yes, ma'am.
Okay. So we have seen only what are equivalent matrices and similar matrices. The remaining topics we can cover in the next session. Okay, I hope these two topics at least is clear for everyone. Make sure you complete this homework which I gave you. Okay.
Ma'am, will you upload the sheet in?
I will upload. I will stop the streaming and I will upload the.
Okay. Thank you, ma'am.
Ma'am, only this is the homework.
There are some